Hi, Professor Herzon. How are you?
I'm good. How you doing, Caroline?
Okay.
All right. Turn off that shine. Is good. All right, so we'll get started here. I just banged out the lecture this morning. So Monday's lecture is now up online. As I said in my email, we're not going to actually include that in the exam because what you'll see today is going to be a continuation of that topic, and so it makes sense just to hold off on it until the third exam. All right, so let me get started here. So we're going to continue with this idea of, we're going to continue discussing the stereochemical outcome of these reactions, which is an aspect of the reactions that we've essentially ignored up until this point. And the examples we'll cover in literature in lecture today are going to get more complicated. You're going to see this, and we're covering them to sort of illustrate the principles. We don't expect you to memorize the outcomes, nor do I want you to memorize the outcomes, but we do expect you to be able to work your way to the correct outcomes. So when presented with a reaction, and the question is, what are draw out all the stereoisomers formed in this reaction. I'm giving you some principles to remember to help you get there quickly. You're going to see today it's going to get very complicated. And so you can't really rely exclusively on memorization. You really have to get at this mechanistically. So think of today as basically we're going to cover a couple problems. We're going to work through a couple problems that hopefully are illustrative, and then we expect you to be able to extend this to other reactions that I'm not explicitly covering. So just to remind you where we left off, let's go here. So we, I believe the last example we did was dibromination of 1-butene. And so we said that this, let me redraw this. From the side perspective. And I'm going to actually use this perspective today because I think it's a little bit easier to see what's going on. So we said that the two faces of the alkene are equivalent, and so bromine can attack, or Br plus can add to the bottom, to the top or the bottom, and we can draw those two bromonium ions. So all right, so that would be addition to the top face, and we'll call this A. And then the other option is to add it to the bottom face. So Br comes in and we add there. Draw that guy out. Okay. And so I actually, in the re-recorded version of Monday's lecture, which for those of you that are coming in a little bit later is now, I just banged it out this morning. It's online. I dive into this example in more detail than we did originally. But so I'll try and just be concise here. So you form these two bromonium ions. The mechanism of the reaction requires backside attack of Br minus on the bromonium ion. So let me just, this is addition to the bottom face. So Br minus is going to come in and attack this bottom bromonium ion here, or it's going to attack the top one like that, in that fashion. So always attack the more substituted carbon, and it's backside displacement, okay? And so the two products that you end up with are these. That one, and then this guy over here. Okay. And if one rotates the bottom structure in plane by 180 degrees, so hopefully what you can see is that you'll get to a structure like a representation like this. So okay. And what that shows me is that the two dibromides arising from opening of the bromonium ions are enantiomers. You can draw a mirror there, and you can see that it's reflected through, okay? When we had office hours, there was sort of a useful thing that came out of that, I think, which is probably worth mentioning for everyone. When we do these in-plane rotations, the wedges and the hashes, what's a wedge remains a wedge, what's a hash remains a hash. So if I spin the molecule in the plane of the paper in any direction, the hashes and wedges always go with the same substituent. When you do out of plane rotations, that's when they start to switch. So it's something to think about. The other thing that we talked about, which I think is useful, is that rotations of these molecules, the reorientations are not changing the molecule in any way. I'm just changing my perspective, right? When I reflect through a mirror plane, that is changing the absolute configuration of each asymmetric stereocenter in the molecule. And I think a good way to think about it is you can think about the reflection as like a mathematical function. Like a mathematical function, you input x, and then the function gives you y, right? It does something to that value. The reflection is kind of the analog of that in organic chemistry. When I put up that mirror plane, what does that mean? It means that I'm actually going to invert all the stereocenters, okay? But when you do the rotations, we're not inverting anything. Nothing should be inverted. And again, if you really want to, be rigorous and double and triple check your work, for example, assign the configuration of the stereocenter here, right? Assign the configuration of the stereocenter in that alternate representation. It should be identical, right? And so I can do it 1, 2, 3. So this is R. this one should also come up as R, okay? And then when you go through the mirror plane, it should come up as S, okay? So anyway, all right, so that's the outcome with addition of Br2 to a terminal alkene. You form a racemic mixture of vicinal dibromides. And we sort of worked through why that is the case. You get enantiomeric bromonium ions. Because they're enantiomeric, they're equal in energy. The rates of formation of those bromonium ions and the rates of reaction with bromide are identical. And so you get a one-to-one mixture of products, okay? And again, I dive into this in more detail in the lecture video. All right, so now we want to go to cases that are a little bit more complicated. And the one that we'll start with is the easier one. And this is a symmetrical 1,2 disubstituted alkene. And so the first one we'll consider is going to be a Z-alkene. This is the easier example. So substituents on the same side of the olefin. And we're going to say that our model system will be cis-2-butene. Okay. And for the purposes of this chemistry, we'll draw it with the side representation. Okay. And we're going to add Br2 to it. And so the question is, what's the stereochemical outcome? Okay. And again, we can use the shortcut to guide us. So achiral reagent, achiral starting material gives me, if I'm generating stereocenters or chiral products, they have to be racemic. Okay. Just as a little bit of an aside note, this is actually goes, there's a whole subfield of organic chemistry interested in the origin of chirality. So where did the first chiral molecules actually come from? You know, if achiral plus achiral gives me racemic, how do you actually sort of tip it, right? You know, all of our amino acids, you know, are of 1 enantiomer. Sugars, of course, are often as 1 enantiomer. So how did nature actually break from that? And there's a lot of actually I would characterize it as lively debate as to how that actually happened. And a lot of that, there's a guy named Mike McBride who was in this department, and he was one of the people very interested in this question. And you know, there were sort of two competing theories, and the scientist with the other competing theory came to give a seminar, and it was the most entertaining Q&A session I've ever had the opportunity to sit through. Anyway, so we're going to add Br to the bottom or the top, and let me just draw those two possibilities. Okay, so we'll say that attack on the top face, we'll call that A. Attack on the bottom face, we'll call that B. And I'm just going to, you know, I'm sort of cheating on the mechanism here. I'm just going to draw one arrow, you know, not explicitly trying to draw the mechanism, just trying to show where the bromine, the Br plus comes in at. So okay, so this would be path A, and the other one would be path B. Okay. So top and bottom attack. And so the question is, what is the relationship, the stereochemical relationship between those two bromonium ions? Does anyone want to venture a guess?
They're identical, aren't they?
They are identical. Right. Excellent. Hopefully everyone can pick that up. So if I just do an in-plane rotation, let's say of B, if I basically spin B around and I'm trying to draw the coordinates just to help you see which axis I'm talking about. If you spin B around, the methyl groups go down. They're both still, again, in plane rotation. Wedges remain wedges, so the methyls are still up, and it's identical to the structure A. Okay, so these two are identical. Sort of another question is, are they chiral? Or A or B, or we said they're identical. So is A a chiral molecule?
Yeah.
No. Right. Why?
Because there is a plane of symmetry.
Yep. There's a plane of symmetry cutting right down the middle of the molecule, right? And so these are in fact stereocenters, but the molecule has a planar point of symmetry, and so it is in fact meso. Okay. All right. So then we can come in and have our bromide attack. Okay. And we know from the mechanism that it's going to add to the backside of the bromonium ion. The question is, which carbon does it attack? And when you're thinking about that, you want to think about which carbon is more substituted, right? But here the substitution is identical. And so there's an equal probability that it's going to attack either one. Okay. And so again, we can go with the AB sort of nomenclature. Maybe I'll just do, well, yeah, I'll stick with A and B. So we'll go green now. We'll go blue. Okay, so Br minus attacking at either carbon, and then let's just draw the products, right? So basically, we're going to draw product deriving from the A pathway on the left. Oops, shoot. Okay, so this is A, and then B goes on the right. So B goes on the right, so the methyl group is up. Okay, and we get to that structure there. And so question then is, what's the relationship between those two molecules?
They're enantiomers.
They're enantiomers, yeah. So can everyone imagine if I put a mirror plane right here? I don't, in this case, I don't actually need to do any rotations or anything. It's just one's the reflection of the other, okay? But again, let me just take a little bit of a side digression. Suppose that you're not comfortable with all of these rotations, right? and, flipping and turning and everything. And that's fine because that takes a lot of time to be able to do this quickly in your head. The thing to do then is just to assign the stereochemistry. Go through the RNS, and it's slower, but you'll get to the right answer. So if we go and do that exercise, and I'm only going to do this once, but 1, 2, 3, arrow goes counterclockwise, and so that is S, right? 1, 2, 3, the arrow goes counterclockwise, and so that is S, okay? And then if we move to the structure on the right, 1, 2, 3, the arrow then goes clockwise. And the reason I'm able to pull this off quickly is because the hydrogens are going back. So you're sort of kind of already looking along the C, number 4 substituent bond. So this is R. And then 1, 2, 3, also going clockwise. And so this is R. Okay. So, the enantiomer of S is R. The enantiomer of SS is RR, right? And so this, the Kahn-Ingold Prelog system provides a way to cross-check your work. You know what I'm saying? Cross-check your conclusions, because this strips away all the substituents and just gets me to RNS. And if you're claiming that they are enantiomers, then the configurations should be the RNS assignments should be complementary. Okay.
Can I ask a quick question about that?
Yeah.
So if we're flipping over the mirror plane, as long as the stereocenters are opposite in their like absolute configuration, we can say that those molecules are enantiomers. Like,
yep.
In this poem, that's like, we don't have to do any flipping whatsoever. It's just,
yep,
the mirror images are different. Okay, cool.
Yeah. And so like if I go back here, let me just go back a slide. So here I did all the rotations and everything. I did the in-plane rotation to try and get it, oriented as a reflection, right? But you could just basically say, okay, I don't want to do that. I don't like to do that. I don't want to do it. I'm just going to assign the configuration. And so it's 1, 2, 3. And so this is R. And then this one is 1, 2, 3. And that is S. Okay. And so without manipulating or doing anything, you can say, yep, those are enantiomers. Okay. Yeah. So, this is challenging, but the good news is there's ways, you have sort of 2 orthogonal ways to approach the problems. And so you can cross-check your work, and make sure that your 2 approaches are in agreement, which I think is good. So, all right. So, so we said these are enantiomers. Okay. And again, we can dive a little bit more deeply into this. I don't want to spend too much time on it, but you can imagine that the transition states preceding both of these stereoisomers are going to look something like this. And so I'll just redraw the transition state on the side. And so this is delta plus, this is delta minus. And so that goes to A, and then the transition state on, it's actually good that we're doing this, you'll see in a second. The transition state that leads to B is over here. Okay. So those are the tops of the energy diagrams, you know, before I form each of the products from the bromonium ion. And hopefully you can, you know, ignoring what's in the middle, see that those two are also enantiomers, right? And so if I wanted to, this is A double dagger, this is B double dagger. If I wanted to put that on an energy diagram, I would have my bromonium ion in the center, and product A would be over here with some energy. Product B would be over here with the same energy because it's the enantiomer. And then the transition states would be, would be up here and up here. And so this is A double dagger, and this is B double dagger, and they're enantiomers, right? And so their energies are identical. So there's an energy, and they are the same, okay? And so this is exactly this is exactly what we drew out for the last two examples. I've just done it a lot faster here, but the point is that you get a single bromonium ion, you can open on either side, but those two pathways are enantiomeric. You know, the pathways are enantiomeric, right? We can sort of broaden it to say, okay, we're going to include the products and the transition states and everything in between. The pathways are enantiomeric, so they're the same in energy, okay? And so you get a one-to-one mixture. You get a racemate. Okay. All right. So as I said, that was the easy one. Any questions on that? Or we take a deep dive? All right. Put on your scuba gear here. All right. So now we're going to do an E-alkene. And we're going to keep it symmetrical. And we're going to do E2-butene. Okay. And we're going to do the same reaction. So addition of Br2 to this alkene. And the first step will be the formation of the bromonium ions. Okay. And so again, we're gonna draw out sort of all the possibilities so that we can go through this, you know, carefully. So attack from the top, we'll call A. Attack from the bottom, we'll call B. Okay. And I get two bromonium ions. Let me draw them.
Wait, so when we're doing this, we always draw like both paths?
Excuse me,
Like
say
A
it
and
again.
B. Like when we're doing these, like we draw both A and B and then A and B again when we attack with the bromine.
So no, so if we want you to do that, we'll specifically ask you to. I'm going through it so you can sort of see so we can sort of step by step in a step-by-step way arrive at the stereochemical outcome. okay? But as you get more comfortable, so what I would say is initially, yes, draw it out, draw everything out and work through it slowly. As you get more comfortable with it, you can start to condense it and get to the answers quicker, okay? So this is approach of the bromine from the top face, and the bromonium ion will look something like this. And okay, so that is arising from pathway A. And then the other one comes from a bottom side attack, Br plus, and my methyl group is out now. Hydrogen back, methyl group back, hydrogen up, and we'll call this one B, okay? All right. And so this one is a little trickier, as I said. Make sure I drew these correctly. Yeah. Okay. So my question to you is, what is the stereochemical relationship between these two bromonium ions?
They're enantiomers.
They are enantiomers. So if you allow me to rotate the one on the right, okay, and I'm going to rotate it 180 degrees in plane, okay, what I end up with is this representation. Okay. And hopefully that makes clear that those two are mirror images of one another, and you could try and superimpose them. They're non-superimposable, so they're enantiomers. Again, if you are not following or you're unsure, what I would say is you can go through and assign priorities to each carbon in each of the bromonium ions, and you should end up with an enantiomeric relationship. And I'd encourage each of you to do that. You know, even though it's a cyclic structure, you count this as one. Looking at this carbon on the left, 1, 2, 1. You can't see where I'm pointing, 2 and 3, and you can assign the configurations in that way. Okay. So they're enantiomeric bromonium ions, and we're then going to consider what happens if I open these up. Okay. And so this is where it's going to get a little complicated, and where as you get more comfortable with these structures, you can hopefully, you know, shortcut some of this. All right. But I would add that, you know, this is still something that like gets me tied up in a mental knot. And, you know, we have instances in lab where we're, you know, making compounds that end up having these types of symmetry elements. And, you know, sometimes the only way to really get to the answer is to work through it. So, all right, so I'm going to redraw both bromonium ions over here. So, and I'm going to use a similar representation for them. And we'll go like that. Okay. So messed it up. Okay, so the one on the left is A, the one on the right is B, okay? And then in the second step of the reaction, I have Br minus come in and attack. Okay, and just like in our last sort of example, the carbons aren't differentiated. And so they have the same substitution pattern. And so I have to consider attack at either carbon. There's no good reason to attack the carbon on the left over the one on the right and vice versa. So we'll go with this again. We'll do the AB sort of nomenclature. Okay. Let's draw the products. So starting with the bromonium ion on the left, attack via the green A would give me something like this. All right, so this would be A. And then attack via the green B would give me something like this. Okay. And then the question that I will put to you is, what is the, let me make sure I drew these correctly. Okay, I did. What is the relationship between these two structures? This one's a little trickier.
They're identical.
Yeah, they are identical. Okay. And so the way to see that is to do now an out of plane rotation. Okay. And the out of plane rotation is a little more complicated because we're going to have to switch the hashes and the wedges. So I'll draw my axis for you. And then the way that we're going to rotate this is by flipping over like that. So flipping from sort of right to left. And what I end up with is then this representation. So BR, okay. So the other thing that I would add is that when I do 180 degree out of plane rotation, the bonds that are in the plane of the paper wind up in the plane of the paper. So that part is nice, and you can sort of retrace that skeleton, you know, without thinking too hard about it. You just need to pay attention then to your hashes and wedges. And again, the easiest, you know, approach it bit by bit. So let's just say, okay, all right, I got to figure out what's going to happen with the hashes and wedges, but you know, I can draw them in without specifying what's at the end. Okay, because I know that, you know, the carbons are still tetrahedral, of course. So that kind of gets us a little closer. And then we can say, okay, what's going to happen here? So this methyl group on the right is pointing back, and so it's going to be pointing forward in following that rotation. Okay, the hydrogen that's adjacent to it here is pointing up, so it's pointing back following the rotation. And the methyl group on the left ends up pointing back, and the hydrogen's coming out. Okay, and so then hopefully you can see that these are in fact the same compound. You don't have to do anything else. You can just take one and put it on top of the other. And finally, I would ask the question, are those molecules, one, do they have stereocenters, and two, are the molecules chiral?
Professor Herzog, can you repeat the question, please?
Yep. One, do the molecules have stereocenters? Two, are the molecules chiral?
And this is for like AA and AB, or is this for?
This is for, I'll box it, for this structure here. Yep.
Okay.
There are stereocenters, but not chiral.
Yeah. This is, because we said that they're the same, this is a meso compound. So it has stereocenters, but the molecule is achiral. It has a planar point of symmetry. And if I'm not going to do it explicitly, but if you rotate about this bond in the box structure by 180 degrees, you can get everything to line up, and you'll see that there's a plane right down the middle. Okay. And so what about bromonium ion B? So let's just make a little room here. Ring opening through pathway green A will give me this. And then ring opening through pathway B will give me this. Okay. And the question becomes then, what's the relationship between these two molecules?
They're identical as well.
Also identical. Yep. Also identical. So same type of operation. If we rotate, say, structure B by 180 degrees about that y-axis. So that's an out of plane rotation. So the substituents on the at wedges and dashes are going to switch. And if you work through that, you'll see that they're the same. They're identical molecules. Okay. So we can basically maybe just think about structure A for now, this one. And what I would say then is, what is the relationship between these two A's?
Identical.
Yeah, they are identical, right? So if we take the A on the right and rotate in plane by 180 degrees, you have the same molecule as on the left. And we already established that the molecule on the left is meso. And so you basically, from all of this, all this complicated analysis, the answer is you end up with one compound and it's meso. Okay. And so I can just redraw that up here. Okay, and that is the product, the product of the addition of bromine to trans 2-butene. Okay, and we said that for the Z isomer, the example that we did before, we got a mixture of enantiomers. But for the E isomer, I'm getting just the meso dibromide. And so the question is, why is that the case? And the answer is it relates to both the symmetry of the molecule and the mechanism. And so, and this is more than you need to know, but for those of you that are curious, I'll take a moment to explain it. So basically the bromine associates with one side, you form the bromonium ion from one side of the alkene. That backside displacement is technically the bromide opening, the backside displacement is technically an inversion of one of the carbons, okay? But the other carbon has not changed its configuration. And so if you trace that back to this guy here, to the E-olefin, you know, if we just think about sort of the planar geometry of those two carbons of the alkene, they have the opposite geometry. And that logically extends then to their tetrahedral geometry. So if I invert one of them, I'm going to give them the same configuration. And so that's why you go, you know, from the trans isomer to the meso. And then for the E isomer, where you're starting with the same geometry at both carbons, you know, the mechanism's the same, you're going to do an inversion at one of them. And so you end up with the DL isomers, okay? So just pausing for a second. This probably seems very complicated. It is, even though this is a simple molecule, because of the symmetry of the alkene and the symmetry of the reagent. So you're adding the same substituents. You get into these really sort of detailed, you can get into these really detailed analyses, okay? What I would say though is it's going to be easier for most, this is like the hardest example. And this type of example does crop up in more complex settings. This is what I was referring to when I said, you know, sometimes I have to think through this stuff and some of the molecules we're making, but it's essentially, it's complicated because there's so much symmetry in the reagent and the starting material. Most instances are not going to be this complicated. So, all right. So I just want to comment on a couple. We've got 3 minutes. I just want to comment on two things. So one is the sense of addition, and we touched on this with the bromonium ion opening. So that occurs by backside displacement, and we refer to that as a net anti-addition. It's a little tricky to see in an acyclic substrate, but if, for example, I did cyclohexene and I added Br2 to this, I would get to this dibromide, and this is formed as a racemate. Okay, so you know, a good thing to do here would be to work through this and get yourself to the racemate. But it's formed as a single diastereomer, which is the trans isomer. So the bromines are on the opposite side of the ring. If you had the bromines on the same side, that would be the cis isomer. And we don't get that because of the mechanism. So the mechanism requires backside attack on that bromonium ion intermediate. That always leads to a trans disposition of the bromides. And that still occurs in acyclic systems, but then it's, you know, it's harder to see because you don't have the ring. Okay. There are other reactions that proceed by cis addition, and the most important one by a large margin is hydroboration oxidation. And so if you imagine hydroboration oxidation of just cyclohexene, you would get to this type of structure. Because there's no other substituents on the alkene, you don't really have cis trans isomerization or isomers. But if you had a substrate like this, and you did a hydroboration, there is a particular stereochemical outcome that would arise, and it would be this one. Plus minus, okay? So we'll pick up with this one, with this example after the exam, but I know you'll probably be studying for the exam, and then you'll probably not want to be studying. But if you do have some time, you might give this this hydroboration reaction some thought, because this is actually a very, very important example, because what I can do is essentially set two stereocenters in the molecule with control of relative configuration, the boron, and therefore the oxygen reliably attached to the less substituted carbon. And so there's what we call regiochemistries. It's a regio-controlled reaction. It's a very powerful transformation when you implement this in more complex settings. So, all right. So just before everyone signs off, just a couple comments about the exam. I've gotten emails from some of you, related to your Friday schedules, and happy to accommodate, but I need to hear from you. No post facto, I didn't have enough time. So please, I will accommodate, but I need to know before Friday. And we'll just set it up so you have the same amount of time as everyone else. And then for the students that are authorized to get special accommodations, extra time for the exam, if you would like that extra time, I will of course honor it, but you need to reach out to me. Otherwise, I will expect that you will, turn in your exam sort of at the usual time. So that it's up to you. If you want the extra time, you can have it. But again, in either case, please, we need to hear about this before the exam, so there's not a lot of confusion after the exam's been administered. Okay. And so yeah, I'll end there. I'm gonna I'll do office hours. I'm gonna sign off. I think the problem with the recordings is that I'm pausing and stuff between the office hours, and then it just seems to get lost. So I'm actually gonna stop. I'm gonna let the video convert. That usually takes about 5 minutes, and then I'll sign back in. Okay. So I'm gonna end the meeting, but I will be back, let's say at 10:25, and you can sign back in if you wish. Okay.